Hey friends, hey guys, my name is IBM and I'm still taking you through magnetic fields and electromagnetic induction past paper questions. I think this is going to be part 19. Part 18 stopped on this question here, which was question 54. So part 19 should start from question 55. A horseshoe magnet is placed on a balance. A stiff metal wire is clamped horizontally between the poles as illustrated here. The magnetic flux density in the space between the poles of the magnet is uniform and is zero outside this region. The length of the metal wire normal to the magnetic field is 6.4 centimeters. When a current in the wire is switched on, the reading on the balance increases by 2.4 grams, which means the force on the magnet due to the wire increases, or there's a force on the magnet due to the wire downwards, which means the magnetic force on the wire should be upwards. The current in the wire is 5.6. State and explain the direction of the force on the wire due to the current. Okay, so the current causes another magnetic field, and then the force due to the magnet on the wire caused because there's a current flowing in the wire is actually going to be upwards. That is by Newton's third law of motion. So there is a downward force on the magnet due to the current in the wire. There is a downward force on the magnet due to the current. In the wire. That's why you see the balance reading increases, which means there is a downward force on the magnet due to the wire because the magnet is placed on the balance. But by Newton's third law, by Newton's third law of motion, then the magnetic force on the wire due to the current is upwards. The magnetic force on the wire must be upwards. Okay, so that is in accordance to Newton's third law. Then calculate the magnitude of the magnetic flux density between the poles of the magnet. Magnitude of the magnetic flux density between the poles of the magnet. So, because there is a force in the wire, the magnetic force on the wire must be equal to the change in the weight, which caused a change or an increase in the balance reading. So I will say the magnetic force is going to be equal to the change in the weight. So the magnetic force is given by B, and the change in the weight is going to be given by the change in the mass times G. So the magnetic flux density is going to be equal to the change in the mass, then times G divided by I times L. Making a substitution, the increase in mass was 2.4 grams, so that is 2.4 times 10 to the power of minus 3, then times 9.81 divided by the current which is flowing is 5.6, and the length of the wire in the magnetic field. The length of the wire in the magnetic field is 6.4, which is 6.4 times 10 to the power of minus 2. to change it to meters. So pressing my calculator, I have 2.4 exponent minus 3 times 9.81 divided by 5.6. I'll put a bracket here. 5.6 times 6.4 exponent minus 2. So this is giving us 0.066. So this is 0.066 Teslas. A low frequency alternating current is now passed through the wire in B. The root mean square value of the current is 5.6 amperes. Describe quantitatively. Quantitative means you must quote a value. The variation of the readings seen on the balance quantitatively. Okay, so we know that the peak current of the sinusoidal current is actually root of 2 times the root mean square current. So which is going to be root of 2. Of course, the peak can be positive or negative, so this will be plus or minus root of 2 times the root mean square, which is 5.6, or it is plus or minus 5.6 root of 2 amperes. That is the peak current. From the same expression, BIL equals to mg, or delta M times G, we shall notice that the maximum mass, the maximum change in mass, the maximum mass, I'll call it M max, is going to be equal to, I'm dividing these the two equations using the first one, this one here, and let this be mg, where m is going to be max. So m max over the initial change in mass, which is 2.4 grams, equals to b is the same, so it cancels. L is the same, so it cancels. But the peak current here is 5.6 root of 2, and yet for 2.4 grams the current was actually 5.6. I mean, yes, the current was 5.6. I've just divided two equations because the current is directly proportional to the mass from this equation here. The rest are constants. B, L, and G are constants. So if I try to make M max the subject, you notice that the maximum mass or change in mass is actually going to be 2.4 grams root of 2, which is 2.4 root of 2. 2.4 root of 2 is 3.39. So that is 3.39 or 3.4. So this is going to be plus or minus 3.4 grams. That is the maximum mass. Then they want us to describe the variation. So the mass changes between, the maximum change is between positive 3.4 grams up to negative 3.4 grams. So total change in mass is going to be positive 3.4 minus negative 3.4, which is the same as 2 times 3.4, which is equal to 6.8 grams as total change. So the new increase in mass, the new increase in mass changes between positive 3.4 grams to negative 3.4 grams, and total change in mass is 6.8 grams. Okay, so that is being quantitative. A uniform magnetic field of flux density B makes an angle theta with the flat plane PQRS as shown in the figure. The plane PQRS has area A. State what is meant by magnetic field. Of course, this is a region of space where a moving charge may experience a force. A force is experienced due to a current carrying conductor. A region of space where a moving charge may experience a force. It's a region of space where a current carrying conductor experiences a force. It's a region of space where a force is experienced due to a magnetic pole, and so on and so forth. So there are different ways of defining a magnetic field. I will just state the simplest. A region of space where a moving charge may experience a force. Okay. An expression in terms of A, B, and theta for the magnetic flux through the plane PQRS. So, of course, we need to find the magnetic field perpendicular, the component of the magnetic field perpendicular to PQRS. Since theta is the angle between the plane or the area and the magnetic field, then resolving perpendicular to this area is going to be B sine of theta. So the component of the magnetic field perpendicular to the area is going to be B sine of theta by resolving. Therefore, it means the force, the magnetic flux phi, is going to be equal to B times A sine of theta, where theta is the angle between the field and the area. We resolve perpendicular to the area. A vertical medium window frame DEFG has width 52 centimeters and length 95 centimeters, which means the area is going to be 0.52 by 0.95 meters squared. The frame is hinged along the vertical edge DG. The horizontal component BH of the Earth's magnetic field is 1.8 times 10 to the power minus 5 teslas. For the closed window, the frame is normal to the horizontal component BH. If the window is closed, its frame is perpendicular to the horizontal component, so it means the magnetic flux linkage is maximum. The window is opened so that the plane of the window rotates through 90 degrees. That therefore means when it is opened, the magnetic field, the plane is parallel. The plane is going to be parallel to the Earth's magnetic field, so the magnetic flux linkage is going to be minimum or zero. Explaining why when the window is opened, the change in magnetic flux linkage due to the vertical component of the Earth's magnetic field is zero. Okay. So the plane of the frame is always parallel to the vertical component, because the horizontal component BH is that for the closed window, the frame is normal to the horizontal component BH. When the window is closed, the frame is normal to the horizontal component. That means whether it is closed or it is opened, it is always parallel to the vertical component. So let's say that the plane of the frame is always parallel to the vertical component, whether it is opened or closed. So the frame of the, no, not the frame, the plane of the frame. So because when the plane is when the window is closed, its plane is perpendicular to the horizontal component. That means the vertical component is always along DG or it's along EF. So whether it is opened or closed, the vertical component is always parallel to the flame. So the plane of the frame is always parallel to the vertical component. The vertical component the plane of the frame is always parallel to the vertical component, that is whether closed or open. So if this is the window, the horizontal magnetic field always makes 90 degrees the frame. That means the vertical component of the magnetic field, this was the horizontal component BH. The vertical component of the same is always going to be parallel to this flame. So the vertical component B vertical will always be parallel to the flame. Therefore, the flux linkage is always going to be minimum. Is going to be minimum in that orientation, whether closed or it is open. So flux linkage, flux linkage. So flux linkage due to the vertical component is always 0 or minimum due to vertical component is always 0. Because the window is already in the vertical plane, it opens in the horizontal. So in the vertical plane, the vertical component of the Earth's magnetic field is always going to be parallel to the frame of the window. So the flux linkage is minimum, or it is approximately 0. Calculate for the window opening through an angle of 90 degrees the change in magnetic flux linkage. So the flux linkage is going to be equal to, remember we said flux linkage is BA sine theta. BA sine theta. Now theta changes through 90 degrees. So this is going to be B, and B is 1.8 times 10 to the power of minus 5 Teslas. Then A, the cross-section area is 0.52 by 0.95. 0.52 by 0.95, and then this is sine of 90. So we check this with the calculator. So 1.8 exponent minus 5 times 0.52 times 0.95 sine of 90. Of course, sine 90 is 1. So this gives us 8.9 times 10 to the power of minus 6 Weber. 8.9 times 10 to the power of minus 6. State Faraday's law of electromagnetic induction. So we say that the magnitude of the induced EMF is directly proportional to the rate of change of the magnetic flux linkage. The magnitude of induced EMF is directly proportional to the rate of change of magnetic flux linkage. The window in B is opened in a time of 0.3 seconds. So it just changes from vertical to, it just moves through 90 degrees. That is from maximum magnetic flux linkage to 0. So the time is not divided by 2. Use your answer in B Roman 1 to calculate the average EMF induced in the coil. So the time for the change of magnetic flux linkage is 0.30 from maximum to 0. So the EMF, we know that EMF equals to the rate of change of flux linkage. And the flux linkage steadily decreases to 0 in a time of 0.3 seconds. So the EMF is going to be just change in flux divided by time. And the change in the flux, I think this was 8.892 times 10 to the power of minus 6. I'll use a more exact value. So this is 8.892 times 10 to the power of minus 6 divided by the time, which is 0.30. So this is going to be divided by 0.3, that is 2.96 times 10 to the power of minus 5, or 2.9 times 10 to the power of minus 5 volts. A particle has mass m and charge positive q and is traveling with a speed v through a vacuum. The initial direction of travel is parallel to the plane of two charged horizontal metal plates as shown in the figure here. Okay. The uniform electric field between the plates has a magnitude 2.8 times 10 to the power of 4 volts per meter and is 0 outside the plates. The particle passes between the plates and emerges beyond them as illustrated there. Explain why the path of the particle in the electric field is not. Of course, in the electric field it is not. Reason being, in the electric field, the direction of the force does not change. The direction of the force is always perpendicular to the plates, not perpendicular to the direction of motion of the particle. Therefore, the force does not cause centripetal force. Unlike in the magnetic field, where the force is always perpendicular to the direction of motion of the particle, in an electric field, the force is always perpendicular to the plates. In the uniform electric field, the force is always in the same direction, or the force is always parallel to the field or perpendicular to the plates. And therefore, there is a constant speed parallel to the plates. Of course, the speed parallel to the plates remains constant because the force is perpendicular to the direction. I mean, the force is perpendicular to the plates or is parallel to the field. So because the speed is constant parallel to the plates, the force does not also provide centripetal force. The path is not actually circular, it is in fact parabolic. So the electric force is in the direction of the field. Because the particle was positive, the electric force is always going to be in this direction here. The electric force will always be in the direction of the field. So the force on the particle is always in the direction of the field. It is not perpendicular to the direction of motion of the particle. So there is an acceleration, constant acceleration in the vertical, and a zero acceleration in the horizontal. The electric force is in the direction of the field, in bracket normal to the plates, or perpendicular to the plates. Normal to the plates. There is a constant speed, or you could say there is a constant speed parallel to the plates. In other words, there is no acceleration in the horizontal. there is a constant speed parallel to the plates. But the speed is not constant perpendicular to the plates. So the force does not provide centripetal acceleration, or does not provide centripetal force. Thus, the path is not circular, but it is actually parabolic. So the electric force, if this was a negatively charged particle, the electric force would be towards the positive plate, continuously towards the positive plate. There is an acceleration in the vertical, which means the speed in the vertical changes, but the speed in the horizontal does not change. The speed parallel to the plates is constant because there is no acceleration in the horizontal plane. So the electric force will not provide centripetal force. However, the path is actually parabolic, not circular. A uniform magnetic field is now formed in the region between the metal plates. The magnetic field strength is adjusted so that the positively charged particle passes undeviated. So now we have added the magnetic field, and the particle is passing undeviated. State and explain the direction of the magnetic field. So I've already mentioned that the particle is positive, so the force due to the electric field is actually downwards. The force to the electric field is downwards. I've called Fe, which means for no deviation, the force due to the magnetic field should be upwards. And if the force due to the magnetic field is upwards or up the top of the page, the particle is positive, so the second finger points in the direction of a positive particle. With the thumb pointing upwards, the first finger will point into the page. So if you have your page, you notice that the magnetic field is going to be into the plane of the page. Okay, so we shall say that the electric force is downwards. The electric force is down the page. It's down the page. For no deviation, the force due to the magnetic field must be in the opposite direction. Must be in the opposite direction to the force due to the electric field. The force due to the magnetic field must be in the opposite direction to the force due to the electric field. And so the magnetic force is up the page. The magnetic force is up the page. Now, by Fleming's left-hand rule, by Fleming's By Fleming's left-hand rule, the magnetic field is into the page. Is into the plane of the page. The magnetic field is into the plane of the page, and that is what we have illustrated there. Note that the electric force on a positively charged particle is always in the same direction as the electric field. That's why we said the electric force was downwards, because the charged particle was positive. If the particle was negative, the electric force would be in the opposite direction, so it would be upwards if the charge was to be an electron. Okay, the particle has speed 4.7 times 10 to the power of 5 meters per second. Calculate the magnitude of the magnetic flux density. Explain your working. So we know that for no deviation, the magnetic force was equal to electric force for no deviation, which therefore implies that BQV is equal to Q times E. And if you try to make B the subject, B is going to be equal to E divided by V. This is going to be E, which is 2 point. The particle, so we're talking about the same particle, the electric field strength was 2.8 times 10 to the power of 4. So this is 2.8 times 10 to the power of 4 divided by 4.7 times 10 to the power of 5. So 2.8 exponent 4 divided by 4.7 exponent 5. So that is 0.059, or it is 5.96 times 10 to the power of minus 2, or 6.0 times 10 to the power of minus 2 Teslas. The particle in B has a mass m, charge positive q, and speed v. That is the particle in part B. Without any further calculation, state the effect, if any, on the path of the particle that has m, same mass, same magnitude of charge but opposite sign, and same speed. Of course, for no deviation, the speed should be equal to E over B. So since the magnitude of the speed is the same, even if the sign is different, there will be no change, or it will still be not deviated, no change, or you can say still not deviated. Okay, same mass as before, same magnitude of charge, but the speed has been doubled. Doubling the speed, if you look at the equation, BQV equals to Q times E. Doubling the speed means that the magnetic force has been doubled. The magnetic force has been doubled. In other words, this will be BQ times 2V. The magnetic force has been doubled, so now the magnetic force is greater than the electric force. So the particle is going to be deviated in the direction of the the magnetic force, which is upwards. So this one is going to be deviated upwards. Deviated upwards, or towards the top of the page. The mass is twice m, charge is positive q, then this is, you notice that for no deviation v equals to E over B, so changing the mass does not affect as long as the speed is the same. So still there will be no change, or you can say not deviated. So there will still be no change, or it will be not deviated, because the condition for deviation is V equals to E over B. So changing doubling the mass has no impact. So to just sum this up, the effect on the path is deduced from the relationship that V equals to E over B. So the path does not depend on the mass, or does not depend on the sign of the charge. Also, doubling V implies that the magnetic force has been doubled. Therefore, the magnetic force is greater than the electric force. So there's a resultant force in the direction of the magnetic force, which was upwards. Therefore, it's only when we change the speed that the particle there is deviation in the direction of the magnetic force. I think that should be part 9. See you in part 20. Bye bye.